Today we'll be learning about parametric equations, and I'm going to start with an example that lends itself to setting up a set of parametric equations pretty well. So here's the situation. We've got a car and it's driving forward at 5 meters per second. It's about to drive off the side of the building. It's a stunt car or something. And the building is 50 meters high, and we're just going to follow the path of that car. And so the first thing I'm going to do is kind of set up an x and a y-axis. It makes sense to have the x-axis be the ground, and then the y-axis we'll put right here. And we'll have the car kind of start its trip right as it leaves the top of the building. And let's say that if this is 0, 0, we'll say that the edge of the building is 10 meters from 0, 0. So we can picture that car is going to zoom off and eventually hit the ground. And so we've sort of got a horizontal movement and a vertical movement at the same time. And that's what parametric equations are good for, is describing that. And so the horizontal movement is just going to be kind of affected by that speed that it's traveling, right? Assuming no air resistance, it begins at the 10-meter mark, and it is adding 5 meters per second, and maybe we could call t our seconds. So t is actually what's going to be called our parameter in parametric equations. T is going to stand for our time in seconds. And then the falling of the car is going to be affected by gravity. Here on Earth, gravity in meters per second squared is negative 9.8 meters per second squared. In a lot of physics class, they'll just round that to negative 10 meters per second squared just to make calculations easier. And so if that car is starting up at 50 meters high, it'll be 50 minus. Now there's a thing in physics, and it's difficult to explain without calculus, although I could try if you're interested. There's a 1/2 involved here, so we could talk about that more later. So we're going to take 1/2 times that acceleration of gravity times the t squared. The t has to be squared because the seconds are squared in that acceleration of gravity. So that's how we would find out the position of the car vertically. And so that's going to lend ourselves to making equations for the x position with respect to time and the y position with respect to time. And this is a set of parametric equations. So again, our x of t was 10 plus 5t, and y was 50 minus 1/2 of 10 t squared. Now, if you're going to graph a set of parametric equations from scratch, your table's going to look a little different from usual because we have 3 variables. We've got the parameter t, and then we've got the x and the y positions. So t is actually going to be the first thing that you plug in. And since t stands for time, I don't think it makes any sense to use any negative t's in this case. So maybe we'll just see what happens when the time is 0 seconds, 1 second, 2 seconds, 3 seconds, however many seconds you think it'll take for that car to hit the ground. And so we'll find the horizontal position by plugging into that x equation. 10 plus 5 times 0, 10 plus 5 times 1, 10 plus 5 times 2, and so on. And that shows how far horizontally this car is going to be after 0, 1, 2, 3, 4, and 5 seconds. And then we'll do the same thing with the y equation. Again, we're plugging in the t values, so 50 minus 5 times 0 squared. 50 minus 5 times 1 squared. 50 minus 5 times 2 squared. And it looks like after 4 seconds, that car would be below ground. Maybe it crashed and made a crater into the ground. Probably not, but if it could keep on going, it would be below ground. Maybe a body of water or something. All right, so then if you went to the graph, you would really just be graphing these points, right? But a lot of people would then label next to those points the t value at each of those points, just as like a little bit of side information. Now, when they ask you to start solving problems, like for example, if we wanted to know exactly when it hit the ground, when did the car hit the ground, we just need to keep in mind that the ground has a y value of 0. And so we take our y equation, the ground has a y value of 0, we plug in a 0, let's go ahead and solve that. So we'd subtract 50, divide by -5, and we'd take the positive version of that, so the square root of 10 is where it's going to hit the ground, which is at about 3.162, which kind of makes sense, right? At a t value of 3.162, that's where we can expect it to be at 0 for the y value. Now, if we plugged in a 3.162 in for the x value, 10 plus 5 times the square root of 10, about 25.811. So then we know where the car is going to land on the ground. So all of these things we can kind of use our algebra skills to figure out exactly what's going to happen to the path of that car. Now, when you do graph those ordered pairs, when you go to putting those ordered pairs on the graph, one other thing that I want you to make sure you do is these graphs have directionality. Because of those t values, because we have t equals 0, like I said, sometimes you'll label these as t equals 0, t equals 1, t equals 2, t equals 3. What I want to see is those directional arrows on there so that you're showing me how that t shows up. And then what I also wanted to point out is that you are able to make this into just a good old-fashioned parabola equation by doing some substitution. Can you imagine if you solved this equation for t, and then substituted that into the other equation for t, it would wind up looking just like this, only now t has kind of disappeared and we just have an equation in terms of x and y. That process is called eliminating the parameter because there are no more t's. T is the parameter. It might be a simpler way to write the equation, but we do lose a little bit of information. First of all, we lose the element of time. I could not tell you what's happening at time equals 2 seconds anymore. I also lose that directionality. I wouldn't know if the car was traveling this way or this way because I've lost that time element. It's also harder to sort of restrict the domain because if I restrict the domain according to the stopwatch on the time, then I can say that it starts here and it ends here and that's the end of the path of the car. On here, I'm going to have to work a little harder at that, talking about the x domain. So a lot of the times parametric equations are just more convenient, especially for physics type problems. Now the parameter t doesn't always have to be time. It could be an angle, it could be a lot of different things. So the parameter can just be like a third variable that affects 2 other variables. The next video you can watch will show you how to get this all entered into your TI-8384 calculator.